Assalamualaikum everyone. My name is Tamanna Yasmin. Now I'm going to give an explanation about our assignment topic. Our first question is about a block diagram. I was tasked with the sketching the overall system architect. The core of the system is data flow. It starts with the four RFID sensor which detect passenger crossing the yellow line. Their analog signals are converted into digital data by ADC or analog to digital converter. The digital data serves two purposes. First, it goes to the passenger direction logic block, which is a simple circuit that checks if more than three sensors are triggered at once to the sound of the alarm. Second, it increments the main synchronous counter, which keep the total count of the people on the platform. The counter's value is crucial. It sends a DAC to convert back to an analog voltage for control room display, and it is the primary input for the finite state machine or FSM. The FSM is the brain of the operator. It uses the counter value to decide whether to keep the gate open or close between IDL check open and close state. Finally, the 555 timer provides the clock close, the synchronous everything, the FSM, and the logic ensure the inter-system operation is in a good manner. And for question 2, I designed the logic for the finite state machine that counts the platform gate. The FSM has four states. It starts in IDL waiting for activity. When the counter is greater than zero, it moves to check. In the check state, it decides the next action. If the platform is full, meaning the counter has reached the 10, it is goes to close to gate. If not, it goes to open the gate. The system also close after 20 tickets are issued for the day. So while the open state, it wait for a special dance signal for the counter. Once the dance signal is received, it transition to the closed state and finally back to IDLE. I translate I translate this logic into HDL code. The finds the state use. The code finds the state use a sequential block to handle state transition on the clock edge and a combination block to define the output, which is simply to open the gate only when the FSM is in the open state. This creates a clear, reliable control flow for the gate mechanism. Question 3 focus on the immediate safety feature, triggering an alarm if more than three people cross together. Since we have four sensors, the condition for alarm is simple. It must trigger only if all four sensors are active. The Boolean expression for this just a four input AND gate. The requirement was to implement this using only NAND gate. Since a NAND gate is a universal gate, we can build any other logic function from it. To create a NAND function from NANDs, you simply invert the output of a NAND gate. So I decide circuit where the four sensor signal are fed into a sing, single four input NAND gate. The output of the gate is the fed into both input of a second NAND gate, which act as the inverter. The final output gives us our alarm signal, which is high only when all four inputs are high. And for question 4, with my ID number, my O is 0. So it replaced with X plus Y plus Z, that is 27. So my P is 25. This gave me a target frequency of 255 Hz and a duty cycle of 75%. I choose a 50 microfarad capacitor for option, as it would lead the most practical restore value. Using the standard stable mode formula for timer, I calculate the combined resistance value used to achieve 255 hertz with the capacitor. Then, using the duty circle formula, I set up two equations to solve for two restore R1 and R2. Calculate give me the value um give me the value of 56 ohm for R1 and 28 ohm for R2. In a real circuit, I would use the closed standard resistor value and draw the standard 55 stable configuration with those components. Here I also design the circuit. And in question 5, they ask us to show how the DA convert the digital calculate convert the digital passenger count in an analog voltage. We have a 4-bit DSA with a 5-volt reference. This means it can replace 16 different values from 0 to 15. The revolution or the voltage change per step in calculate as the reference voltage divided by the number of steps. So 5 volt divided by 16 give us a step size of voltage, and 5 passenger, the digital input is 5, so the output voltage is simply 5 multiply by and also give us a voltage. And for 10 passenger, the digital input is 10, so the output voltage also multiply by 5. My final output is for 5 passenger is 1.5625, and for 10 passenger is 3.1225 voltage. And for question 6, limitation of system. Finally, while the system is functionally sound, it has several significant limitations for a real-world engineering perspective. First, it lacks a mechanism for counting people exiting the platform. The counter only increments, so after 10 people enter, the gate would never open again if everyone leaves. Second, it really is on the perfect RFID reads. In reality, signals can be blocked or missed, leading to incorrect counts. Third, the alarm logic is simple. It assumes people will work in a perfect signal field. A group of three working closely together might accidentally trigger a fourth sensor, causing a false alarm. Fourth, using a simple DSA to send data to control room is prone to noisy and signal over a long distance. A digital communication method would be more good way. Finally, the 200 ticket daily limit is not practical for public transport system, and the highlights that the system's logic is too unreal for real world passenger flow. A more flexible and fault tolerant design would be necessary for actual development. Thank you, everyone.